Okay, we're live. Hello, everyone, and welcome back to the workshop series with Stacks. I'm James from DoraHacks. This is for the BUIDL Battle Hackathon, which is live now, and there are just about 12 days left for submission. So you can head over to the link in the description to register and submit your projects to that. We've got a 90K prize pool. This is a BUIDL-focused hackathon. Super excited to be supporting it from DoraHacks. And there's Adam. Hey, Adam.
Hey, everyone.
Thanks for jumping on. And I'm here with Haardik from Learn Web3. How are you doing, Haardik? Thanks for joining us.
I'm good. Thank you so much for having me.
So I don't know if you want to say anything else at the start, Adam, here, or we can just hand over to Haardik for the workshop.
Yeah, not a whole lot more to add on my side, just that we are excited for day 2 to kick off, and we have Haardik up here for our 4th workshop. So without further ado, I will let Haardik take over.
Sure.
Perfect.
Okay, great. Good. I'll pop me and Adam backstage, and I will give you your screen. So the floor is yours, Haardik.
Awesome. Cool. Hey, everyone. My name's Haardik. I'm here on behalf of Learn Web3. Today, we're going to be talking about building a payment streaming app. So this is part of the Stacks developer degree that we have over at Learn Web3. And yeah, as I said, so we're going to do our build a token streaming protocol project today. So for those of you who might not be familiar with what this is or what this means, essentially what we're going to be building is so like a token streaming protocol is essentially, it's a way of establishing a continuous payment stream between two parties, so like a sender and a recipient. This could be like a employee and an employer, or like an organization giving out grants to a grantee, something like that. And the sender typically would start off by creating a stream, a payment stream that defines some sort of time period, the amount of tokens to pay per block to the recipient, like per on-chain block to the recipient, and obviously who the recipient is. And then literally with like every single block that's produced on-chain, the recipient is slowly getting like more and more tokens. They're accumulating more and more tokens from their payment. And then at their will, at any point in time, they can withdraw whatever they're owed up until the end of the time period. So, use cases for this kind of like commonly used in like 2 scenarios that I've seen. It's like freelance work that somebody might be doing for a client, in which case, instead of giving all the payment up front or keeping all the payment until the end, you can kind of create this payment stream, which is flowing, let's say, over like a 1-month period or a 6-month period, whatever. And money is like slowly, being streamed out to the recipient, and they can withdraw whatever amount they've accumulated at any point in time, right? Similar ideology we've seen is like with grants being given out to projects, where we've seen like granting organizations can create a token stream to the project team to pay them out over time, and the recipient can again at any point withdraw the amount of tokens they've accumulated from the stream up until that point, while the remaining will continue getting streamed. So let's get started. So the way this is going to work today is I already have this code written out. So instead of live coding, because live coding can get a little bit tricky with like timings and making sure everything fits properly, what I'm going to do is I'm going to sort of review function by function and like step by step, like key aspects of the smart contract that we've written for Stacks. And we'll kind of like, cover all the functionality. I'll kind of explain it as we go through it. And then towards the end, I'll point you to like, like the full GitHub repo and like the full tutorial you can find on this project, as well as many other projects if you're just learning how to build on Stacks or getting started. Cool. So with that, I'm going to assume you have like some basic knowledge of how Clarity works, just like basic Clarity syntax and stuff. But yeah, with that, so step 1, obviously to like set up a brand new project, right? So we're going to be using Clarinet for this. So it's as simple as saying like Clarinet new token streaming is to like scaffold a brand new Clarinet project, install the dependencies in there, and then we're going to create this new contract we're going to call stream. Then inside the stream contract, now we're going to start going over the code. So we'll set up a little bit of a boilerplate. The key things here is we're going to define certain errors, that will show up in different parts of the code. So, for example, we have the error unauthorized. This is an error that somebody can hit if, like, you try to withdraw money from a stream where you're not a recipient, right? Like that money doesn't belong to you. So you're going to get an unauthorized error, invalid stream ID. If you're talking or like trying to do something on a stream that doesn't actually exist, the stream's still active, and invalid signature. We'll get to those shortly. Apart from that, we've just defined a couple of things in our storage. So just starting off with a latest stream ID, we're going to treat like each stream has a unique ID, and they're just numbers. So we're going to start off at 0, and then latest stream ID will keep incrementing as more and more payment streams get created on the contract. And then lastly, we have this like big storage mapping, which contains all the actual information and details about each stream. So it's a map that takes in the stream ID as the key, and then in the value, it's a tuple that contains all the relevant information. So it's going to have, the sender address, the recipient address, the balance, which is how much money there is locked up in the payment stream. There's the withdrawn balance, which is how much money has the recipient already taken out of the stream. There's the payment per block, how much money is being unlocked to the recipient every single block on chain. And the time frame, right? What's the starting block and what's the ending block for this stream? And this is used like as an analogy to like actual time, right? So instead of saying like, I'm going to start paying you from midnight of 5th March, you correspond it to like a certain block number, like your payment starts on this block number and it ends at that block number. Right, so we're just going to go with this like basic boilerplate down here. Then, once we have that, like the first obvious thing we need to do is we need to be able to create a new stream. So we're going to start off with implementing this function stream2, and it's going to take in 4 arguments from the user. We have the recipient address, we have the initial balance, which is how much money you want to lock up in the stream. We have the time frame, the starting point and the ending point, and then how much money is being released per block, right? So then in our contract, there's a fairly simple function. The main thing that we do is we create this stream tuple that we're just going to put this in our mapping over here. So create this stream tuple that just has all the information, right? Has the sender address, recipient address, balance. Withdrawn balance is 0 right now because it's, the stream is just getting created, payment per block, and the time frame. And then we're going to get like what is the current stream ID, which is just the latest stream ID that we can use. So right now there's like no streams have been created so far. So the current stream ID that we're going to assign this is going to be 0, which is the latest stream ID. And then once we've created a stream, we're going to increment it by 1 later on. But so we define this couple of like local variables. Then we want to take the tokens from the stream creator into this contract, right? So like if I'm going to start a stream of like 1,000 stacks tokens to be paid out to Adam over the course of the next 24 hours or something, what I need to do is I need to send those 1,000 tokens over to this smart contract, and then this contract, like Adam can come and withdraw his tokens from this contract at any point over the next 24 hours or even later. So we're going to just do a stacks transfer. We're going to transfer the initial balance from the sender, from the creator of the stream to our own contract. So we're going to transfer tokens from the stream creator to this contract, and then we're just going to do a map set. So we're going to update. We're going to in our streams map, we're going to add on the current stream ID the stream object that we've created. We're going to increment the latest stream ID by 1. So like latest stream ID equals current stream ID plus 1. And then you just return and you okay, this is the ID at which the stream got created. Cool. It was a fairly straightforward function, nothing too complex going on here. Mainly, we just take tokens from the sender, keep it with ourselves, and just put stuff in our storage. Once we have a stream, another thing the sender might need to do is we're going to do a refuel function. What a refuel function does is, since the stream may start in the future, right? The creator, they might not want to lock up their Stacks tokens immediately at the time of creation, or the thing they're paying for, they might get extended, right? So like if you're like a freelancer working for a client, maybe your scope of work gets extended, you have to work for some more time, and so your payment stream needs to be extended. So the creator needs a way to be able to like add more money to that payment stream. That's what we call like refueling the payment stream. So to refuel, the creator is going to tell us the stream ID that they want to refuel and the amount of tokens that they want to add to the stream. So then based on the stream ID, we're going to load the stream details. So we're going to do like a map get from our streams mapping for the stream ID. And then if this doesn't exist, like the stream ID is invalid, this is where we throw the invalid stream ID error. Once we've loaded the stream, then we're just going to assert that the person who's calling the refuel function, they are actually the sender of the stream. Right? It's not like some random person trying to mess with a payment stream somebody else created. It must be the person who started the payment stream. If this is not true, then we throw the unauthorized error. But if all that is good, if it is the sender and the stream ID is valid, then we just transfer the additional tokens from the sender to this contract. So whatever amount they want to refuel it by, we just do a Stacks transfer for that amount from the sender to our own contract. And then we update our streams mapping. We do a map set on the streams mapping for the stream ID. We just update it where we increase the balance of this payment stream by whatever the previous balance was plus the new amount. And then we just return. Okay, so fairly simple refuel function. It's very similar to creating a new stream, except this time we're just updating a stream that's already created, and all we're really doing is we're just increasing the amount of balance of that payment stream. Other than that, it's mainly just a Stacks token transfer from the sender to the contract. Once refueling is done, then once a stream is created, the recipient can withdraw any tokens available to them up until that block. So like if I create a stream right now, over the next 24 hours, 5 minutes from now or an hour from now, you can withdraw whatever partial amount of that money you've accumulated at that point. So the recipient can withdraw any tokens available to them up until the current block, basically. But before we implement the withdraw function, we need a couple of helper functions to make things easy. So we're going to do a couple of helpers. We're going to do a function called balance of, which is going to track, how many tokens the recipient has available to withdraw from a given stream, like currently. So like anytime you call this function, it's going to check like at the current point in time, how many tokens has the recipient accumulated, right? And, like if you call it multiple times over a period, the number is going to keep going up, right? Because over time, you're accumulating more and more tokens. But at a given point in time, what is the balance that the recipient has available and ready to claim and ready to withdraw from this payment stream? And to do that, we're going to use a second helper function called calculate block delta, which is just going to check like how many blocks have passed, if any, since the starting block of this payment stream, right? Like, has the payment stream even started yet? Maybe I create a payment stream that doesn't even start until tomorrow. So 0 blocks have passed so far. So you have like 0 balance. But assuming the payment stream has actually started, then how long has it actually been, right? Like how many blocks have actually passed since then? And based on that value, we can use that to calculate how many tokens you have available to withdraw. And once we know how many tokens you have available to withdraw, then we can implement the actual withdraw function, right? So we're going to go like this. So we're going to implement this function first, then we're going to do this, and then we're going to do this. So starting off with calculate block delta, what we're going to do is we're going to take the time frame of a stream, right? It's like each stream has the start block and stop block. So we're going to take this time frame as an argument, and this is a read-only function. So we're going to take the time frame of a stream as an argument, and then we have the start block, we have the stop block, and then we're going to calculate the delta such that if the block height is less than the start block, which means the stream hasn't started yet, like the start block is at some point in the future, then no blocks have passed yet since the stream having begun. So we just return 0. Otherwise, if the block height is less than the stop, otherwise, the payment stream has started, but now has it ended yet, or are we in the middle of it, right? So if the block height is less than the stop block, which means we're kind of in the middle of the payment stream right now, it's still ongoing, then the number of blocks that have passed, that have accumulated you money, is the current block number minus the starting block number of this payment stream. Otherwise, if the payment stream has started, and also if the payment stream has ended, the whole thing is passed, and you're just claiming it at some point in the future after the payment stream is already over, then the total number of blocks that have accumulated your money is just the total time frame the stream was active for. So it's like stop block minus start block, right? And then you just return this delta from this read-only function. Once we have a way of calculating block delta, then we can do the balance of function, which helps us check the balance for party involved in a stream. So for this, we're going to take in the stream ID, like which stream are we checking for, and who are we checking for, right? Like who's the recipient. So again, based on the stream ID, we're going to get information about the stream from our mapping. The map get streams, get information about our mapping. Then we're going to check the block delta, how many blocks have passed based on the time frame of the stream, and then we're going to calculate the total balance that the recipient has available to them, to like the total claimable balance the recipient has available to them is basically the number of blocks that have passed multiplied by the payment per block for the stream, right? So if I create a stream to send out 100 stacks tokens over 10 blocks, you're basically getting 10 stacks tokens per block, right? So if 5 blocks have passed so far and 10 stacks tokens per block, you have 50 stacks tokens, as part of the recipient's balance. Then if we calculate all this stuff, so this is a total recipient claimable amount so far, but the recipient may have already withdrawn some of that money out already in the past, right? So maybe there's 50 stacks tokens total you've accumulated so far, but perhaps you've already taken 20 tokens out at some point in the past. So we need to check for that. And it checks, so if the who address is the recipient of the stream, then the balance they have available to them in actuality is the total accumulated balance minus whatever withdrawn balance is from that stream. So whatever money they've already taken out of the stream. So total balance minus money they've already taken out. Alternatively, if we're checking the balance of the stream sender, then in that case, it's going to be how much total money is left in the stream minus how much money is going towards the recipient, and whatever is left is kind of extra money they may be added by mistake that they can refund or withdraw back to themselves. Otherwise it's just 0. If it is neither of these cases, if we're just checking a random address, then it's just 0, you have no balance in this payment stream. So you have balance of, and then we have the calculate block delta done. So with balance of, now we know whether you're talking about the recipient or the sender of a stream, how much money do they have available to them? Using these, we can now implement the actual withdraw function, right? Both of these so far were read-only. So it's just like helpers, read-only functions. You can also call these off-chain on like a website to make it, show these things to the user. Then the actual withdraw function, the public function. So you take in the stream ID where you want to withdraw the money from, and then start off doing the same thing, right? Start off with, based on the stream ID, do a map get from our mapping, load up the stream details. If it doesn't exist, then you throw the error invalid stream ID. Once we have the stream, we also fetch the balance of this person who's calling this function using the balance of helper that we wrote. So check the balance of the stream ID and the contract caller, whoever's calling this function. Let me check. Okay, so this withdraw function, it must be called by the recipient of the stream. Only the recipient can withdraw money out of the stream. We're going to write a separate function later for the creator of the stream to like take out excess tokens, but the withdraw function can only be called by the recipient of the stream. So we just assert that the contract caller is equal to the recipient of the stream. Otherwise, you're unauthorized to do this operation. So we throw the unauthorized error. If that's okay, if it is the recipient doing this, then we update, do map set. We update the streams mapping for the stream ID, where we update basically the withdrawn balance for this recipient based on money they've already taken out plus money that they're going to be taking out right now. Right, so money they've taken out in the past and money they're taking out right now as part of this function call. So we update the mapping, and then we do a stacks transfer. So we send tokens, whatever money they have available to claim to them. We send that many stacks tokens out to this person, whoever called the contract, to the recipient of the stream. Right, so money that is within our contract, we send it to the recipient of the stream based on whatever balance they have available to withdraw right now. And then we return. Okay. Similar to withdraw, as I said, we're going to do a refund function for if the creator of the stream accidentally put in excess tokens or more tokens than they were supposed to, or if the payment stream even gets shortened perhaps, then they might have excess tokens left over in the payment stream. So we create a refund function, which again takes in the stream ID. It's going to be very, very similar to the withdraw function. We load up the stream details, we load up the balance, this time of the sender of the stream, how much money they have available to refund to themselves. We load up balance of the sender of the stream, and we just assert that this function is being called by the sender of the stream. Otherwise, we throw the unauthorized error. We also assert that the stream isn't active right now. Right? We assert that the stream is over already, and money left over at this point is what is excess money. Because if the stream is still active right now, then that money is earmarked already for the recipients. You can't just like take money out of that right now. So we assert that the stop block of the payment stream is less than the current block height, right? Which means that the block height being greater than the stop block means the stream is over. If that is not true, then we throw the error that the stream is still active. You can't do this right now. But if the stream is over, you are the sender, then we can update our mapping. We update the streams mapping, and we update the balance, where we remove whatever the balance previously was minus money that the sender is taking out for themselves. And then similar to withdraw, we just do a stacks transfer. We send the balance out to the sender of the stream, and we return okay. Cool. Then we need one more function and this is maybe the most interesting function of them all. We need a way to update. We need a way to update the stream details after a stream has already been created, right? So, for example, maybe your contract gets extended as a freelancer, or or maybe you're bad at your job and it needs to be reduced. Either way, the parties need a way to like update the details of the stream after its creation. But since when we do this, we're talking about a reduction in the amount of money that is going to be paid out, there's opportunity for malicious behavior, right? The opportunity being the sender. If we let the sender, for example, control this entirely, the sender can be malicious and like stop the payment before it's actually supposed to end, and basically like not pay the recipient, and vice versa as well, right? If we give the recipient full control of this, then the recipient can maybe take more money than they're supposed to be able to take. So we need a like two-party consent system. We need both of them to agree to updating the stream details and also what the specific details are, but only one person can be doing the on-chain transaction at a given time. So what we're going to do, we're going to design a system in a way where one of those two is going to simply provide a signature approving, the update to the stream details, and the other person is just going to take that signature and call the actual function on chain. So let's think about that for a second. So for its simplicity, let's say the recipient is the one who's doing the actual on-chain transaction. So the sender is going to send over like a signed message to the recipient, and this happens off chain, right? You message them on like Telegram or something. You send over the signed message, or in practice it would be like on a website, but it sends over a signed message over to the recipient, and the signed message kind of proves that they're providing consent. And the recipient, when they call the on-chain function to update the stream details, they pass in the sender's signature as well, and then the contract can verify the signature as well to know that both parties have in fact consented to this. So how's all of that then going to work? So that was kind of like background context. The way they're going to work is, what we're going to do is we're going to generate we have to generate like this unique hash that the person will be signing over. And it's important that this hash represent information about, what the stream used to be in the past, and also what it is exactly that it is being updated to. You can't just take like an arbitrary signature, right? We need to have a signature that proves they've consented to the specific details of what we're updating the payment stream to. And the way to do this is we're going to take a hash of the stream as it exists, as well as its new fields, like new things that are going to be updated. And essentially, there's two things you might want to update. There's really only two things you might want to update. One of them being how much you get paid out per block, right? Like increasing or decreasing the amount of payment per block. And secondly, the time frame, right? Extending or reducing the amount of time the stream exists for. So we're going to start off by creating this like helper function. So read-only function called hash stream that's given a stream ID, given new payment per block that you want to set it to. And this can be the same as the old one if you don't want to change it. And also the new time frame that you want to set it to, which has the start block and the stop block for the new payment stream. Again, either one of these two can be the same as the old one if you only want to change one of these variables, but we provide both. And then what the hash stream function is going to do, firstly, it's going to load the stream details from the stream ID. And then this whole thing here, this whole long thing here, what it is, it's basically just converting the stream, the new payment per block, and the new time frame. It's taking all of these values, it's converting them to condensing them down to raw bytes, and then it's concatenating them all together. So it's basically just convert it all to raw bytes and merge it all together to form this message. And then we just take the SHA-256 hash of this message. And then this hash of the message is what one of the parties will sign over off chain to prove they've agreed to these specific new terms for this payment stream. Right? Because if they agreed to something else, if they agreed to maybe a different time frame or a different payment per block, this hash would be something completely different. And then when we go to verify the signature on chain later on, it won't verify. They need to agree to these specific terms. So you have this helper that creates the hash for us, and then they do the signature through their wallet, off chain. And then for the flip side, we're going to create again this other helper function to validate the signature. So we're going to take in the hash that it's supposed to be, the hash that they supposedly signed over, which is going to be the payment per block and the time frame and the stream details that they supposedly agreed upon. So the hash of that, and then the signature that the user is providing, and who the signer is supposed to be. Right? So let's say it's the sender of the stream that did the signature off chain. So this would be the sender address, the signature that they did, and the hash of what correctly, ideally, would be the thing they should have signed over. And then we just check. We do a SecP256K1 recover, built-in function into Clarity to basically verify a signature. So you give it the hash and we give it the signature. So if the signature was in fact made over this specific hash, it will return true. Otherwise, it will return false. Sorry, not false. It will return the public key that supposedly signed this message. And then we can use the principal of built-in function to convert that public key into a principal, just like the stacks address. We just want to make sure that this principal is equal to the signer that we expect. If it is something different, that means the data was wrong, or the signature is invalid, or they agreed to some other terms. In that case, the signature overall is not considered to be valid. So combination of validate signature and hash, we can finally create the actual update details function, which brings it all together. So what we're going to do is we're going to give it update details for the stream ID. This is the new payment per block you want to set. There's the new time frame you want to set. This is the signer who did the signature off chain, which is the person other than who's calling this function right now. And also this is the signature that they're giving to us. So based on that, we can load the stream details from our map, map get streams for the stream ID. And then we assert that, we take the hash of the things that, this is being updated to. We use our hash stream helper function. We give stream ID, payment per block, and time frame to recalculate the hash of the terms that these people are agreeing to. And we validate the signature that this is the thing, this is the hash of the new payment terms. We validate that the signature being given to us is actually a signature over this exact hash and not over a different hash for different terms that they may have agreed to. So we assert that the signature is valid and is done by the signer. Otherwise, we throw the error invalid signature. And then we also assert that one of these two cases must be true. Right? We assert or either this line is true or this line is true. What this is basically is just checking that either the sender of the stream is the one who's calling this function and the recipient of the stream is the one who did the off-chain signature, or it's the sender of the stream who did the off-chain signature and the recipient of the stream who's calling this function right now. It can only be one of these two cases. If it's some random third party calling this function or doing the signatures, then we throw the error unauthorized, right? That's not okay. So the signature is valid. If this is fine, then we can go back. We can do a map set, our streams mapping for the stream ID, and we can update it to the new terms, right? We can update it to the new payment per block and the new time frame. Return OK, true. So the overall workflow ends up being something like this, right? What we've enabled ends up being something like this. So let's say Alice creates a stream for 700 stacks tokens to be sent out from 5th March to 19th March, right, over a 2-week period, and marks Bob as the recipient of this stream, right? So Bob starts getting paid these stacks tokens immediately. Every single block that is produced on chain, Bob is accumulating more and more, stacks from the 700 that Alice put up in the stream. Let's say after 1 week, on 12th March, like halfway through the payment stream, Bob decides to do his first withdrawal. And at this point, he successfully withdraws, 350 tokens from the total 700. The stream now also has 350 tokens left over. Now, Bob is doing amazing work, right? Due to Bob's commendable work, Alice decides to give Bob a raise, right? I mean, like a tip or a raise. She increases basically some of the money that Bob's going to get. So what she can do, she can call the refuel function. She refuels the stream and adds another 70 stacks tokens to this payment stream. And Alice then requests Bob to sign over the updated details. She constructs the hash for updated details, which would be, an increased payment per block for Bob. So he constructs the hash, sends it over to Bob to sign it. Bob does the signature and gives it back to her. And then Alice calls the on-chain function to update the stream details. And then the contract, can verify Bob's signature, know that both of them consented to it. It's all good. And then 1 week later, on 19th March, Bob is able to withdraw another 420 stacks tokens, right? So 350 that were left over from the original stuff and 70 that Alice added later is able to withdraw those 420 tokens on 19th March once the stream is over. There's a few improvements and ideas, like for people who are watching this, who might be looking to take inspiration or are interested in this kind of stuff for the hackathon. A couple of things you can improve upon or, add to what we've discussed so far is you can implement support for SIP10 tokens like SBTC to also be streamed to this protocol. The code I showed and the code I was looking over, that is only designed to transfer the stacks like SDX token in payment streams. You can modify the contract, and you can also add support for tokens like SBTC and also any other SIP10 token to also be able to be payment streamed through this way. Secondly, so far we've only really been looking at the Clarity code, the actual smart contract code for this. But to make it actually easy to use, especially the off-chain signature part and updating stream details and stuff like that, you can create a front end around this contract, right? It's like a React app or whatever. You can create a front end around this contract to make managing streaming payments easy to use and also receiving streaming payments easy to use, right? So either way, if you want to create a new payment stream, manage a payment stream, or like if you're on the recipient side of things, like you want to withdraw money out of a payment stream, there should be like a nice little website you can go to, connect your wallet, do all of these things. But yeah, with that, thank you so much. The full step-by-step lesson and the full code, as well as a GitHub repo for this, is available at learnweb3.io. Just go there, go to the Stacks developer degree. You'll find this project in there. There's also many other projects that you can learn from. You're like 5 or 6 other projects, mostly around DeFi, different types of DeFi protocols we built that you can also look at and learn from. But yeah, that's it from my end. Thank you so much for watching if you stuck around this far, and wish you all the best in your hackathon.
Thanks, Haardik, for a great presentation. Fortunately, we haven't managed to connect to YouTube for this stream. So if anyone has any questions, they can put them in the Telegram group, the link to which is at the top of the details page on the DoraHacks hackathon page. So you can jump into the Telegram group. I'd recommend everyone to do that. Anyway, get inside the channel so you can see what other questions are being asked. And if you have any questions for anyone at the Stacks team or for Haardik, just pop them in there and they'll get back to you as soon as they can. Any questions about DoraHacks, obviously you can message at DoraHacks Official on Telegram, any of the other usual channels. So feel free to get in touch or join our Discord through the link on our website. Thanks, Haardik. I'm not sure if Adam wants to jump back in, but we can probably round this up nice and early. But thanks for your time today.
Perfect. Thank you guys so much. And yeah, if you have any questions, feel free to reach out. Thank you again for having me. And I'll see you guys around.
Cool.
Cheers.
Okay. Well, we've got 12 days left for the hackathon. So get hacking and yeah, reach out with any questions. Thanks for your time, Haardik. Let's stay in touch.
Perfect.